All right, chemists. Okay, so welcome to this week's edition of the A-Level Chemistry Masterclass here. And so I want to dive in and do some problems here. Okay, so in complete disclaimer, I mean, first off, yes, I know I have the lockdown hair going. Yeah, I know it's getting worse each and every week. Scratched the lens of my glasses, and so I'm wearing contacts this week, which means that if you see me peering at the screen like this, it is because I'm trying to actually read what's on the screen, because the contacts are actually designed for when I do sports, as in running, not actually looking at a computer screen. So bear with this week, okay? But got to keep going. So anyway, what I wanted to do is I wanted to start off then right on where we left off on last time, question 2. Now, I think I did question 2 last time, and so I wanted to start here, like maybe I ended at question 2. But anyway, this is the one here. We're obviously doing the pH of strong acids and strong bases, just wrapping up this bit. And so what I thought we'd do is we would finish off the module on strong acid, strong base calculations, really easy to do. And then after that, do some past paper questions on it, because you know I like to do past paper questions to help you out as much as possible. And then we'll take a look at weak acids and weak bases. All right, so here we are on this one. All right, so on this one here, let me move my video link button out the way here so we can see what's going on. Too many video link buttons and controls here. Okay, so calculate the pH of a solution formed when 25 cubic centimeters of 0.150 mole per decimeter cubed of sulfuric acid is added to 50 cubic centimeters of 0.1 mole per decimeter cubed sodium hydroxide. All right, so on this one, chemists, this is what I've been saying now for a couple of sessions here, is you need to start thinking like a teacher, right? Like, why are they asking me this? Because they're asking you for 2 reasons. Number one is, do you realize it is a diprotic acid? So over here, all right. Get my board turned on. Right here, chemist, this is a, whoops, hold on. This is a diprotic acid here, okay? So be careful with this one, diprotic acid, number one. And number two, I'm going to state the obvious here, that volumes are additive. And so again, what they're hoping you do on the exam, under the pressure of the exam, is you forget the volumes additive, okay? So anyway, on this one, yeah, give us a head start on this one here. I did write everything out. So I got sulfuric acid and sodium hydroxide, obviously acid-base reaction. Something you probably did at GCSE is going to give you sodium sulfate and water. Now, got to balance it. Now, the tricky bit, again, chemists, is here, look, you know, when you're doing past paper questions, always be thinking, right, what's the tripwire? Well, what they're really asking you is, do you know the charge on sulfate is -2? And so therefore you need 2 sodiums. So it's going to be sodium sulfate, Ne2SO4. So this is balanced, yes. All right then. Now, as I said last time, the very first thing I do is I always write down, hold on, ding, 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 hold on, chemists, am I, yeah, I think I'm good here. Hold on a second, chemist. Got to just try click on one more thing right here. Yep, all right, we're good. Never mind. Is I always write down C and V, concentration, moles, volume, straight off the bat. It's just automatic, okay? So you then put in the data you have, and so the concentration of sulfuric acid is 0.150. The volume is 25 cubic centimeters. Or if it's sodium hydroxide, it's 0.1, the volume is 50 centimeters. So I need to calculate the moles of acid in the base present initially, and the plan for doing this one is to figure out which one is in excess. Okay, so if I do that, take my concentration as moles per volume, rearrange it to get moles is concentration times volume over 1,000. Then I can put the data in, and I'm going to get the moles of hydrogen ions and the moles of hydroxide ions, okay? So moles of acid then would be 0.150 times 25 over 1,000, which is 0.00375. Agreed. Now, chemists on this one, all right, you know when you do a monoprotic acid and just straightforward base, there was like one hydroxide, right? And you just get the moles of acid and the moles of base, and you see, well, which one is in excess, right? Because it's a 1-to-1 ratio, what you're actually doing is you're actually skipping this equation here. Because it's 1-to-1, you just say, oh, this 1 mole of acid reacts with 1 mole of base in your mind when you're doing these, right? But in actuality, what you should be saying is the moles of hydrogen ions equals the moles of base. Now, for a monoprotic acid, this doesn't really make that much of a difference. But for a diprotic acid, it does. Because for diprotic acid, what you got to keep in mind is this, is that H2SO4 is going to ionize. Let me put it down like this. Yeah, it's a strong acid, ionize into 2H plus and OH minus. And it's this extra step, let me move my little video link out the way. It's this extra step here which becomes important when you're dealing with a diprotic acid, because, all right, then you put the number of moles of hydrogen ions you get from the acid into the first equation, right? You neutralize it with the hydroxide ions. Now, this is the trick, right? You got to take the moles of acid and also you got to double it. So 1-to-2 ratio. So when you do that, you double the moles of acid, 0.00375 times 2 is going to give you 0.0075 moles of hydrogen ions, which is actually what is going to react with the moles of hydroxide ions, which is 0.005, right? Now, look at this, you say, right, obviously the acid is in excess. And so you would have step 2, calculate how much acid or base is left over, right? Because obviously what I did is I looked at, hold on. I think I have, and we are at that, looked at, I don't have my pen. All right. The moles of acid and base. So before I even did this calculation, initially present, on the previous slide, I'll take a look at it now, is I just eyeballed it really quick. And you're thinking, yeah, I mean, obviously, there's more moles of acid than there are moles of base. And so this is why I said that the moles of acid is the one that's left over. Okay, if the moles of base was greater, then I would have written down the moles of base is equal to, all right, so I would take the moles of acid minus the moles of base, the larger minus the smallest number, and this is going to give you the moles of acid. All right, so if you're wondering how I knew that, it's just like, well, whichever one was larger, the base, well, then I would take the moles of base minus the moles of acid. Well, because the moles of acid was larger, it's got to be the moles of acid minus the moles of base. Now, you get this bit, right? You say you have 0.0025 moles of hydrogen ions, correct. Now, this is the next bit. The next bit that's a bit tricky is this bit here, chemist, is obviously concentration of acid is the moles of acid, agreed, over, now this is the additive volume. This is the additive volume. All right, so it was 25, I believe it was 25 cubic centimeters of acid to 50 cubic centimeters of base. And so in your note, you're thinking, yeah, additive volume, you need to add them up, okay? And so divide by 1,000 because I need to get from cubic centimeters into decimeters cubed. And so I end up with this number of moles per decimeter cubed. Let me put it like this. Hold on. Keep everything nice and neat. Moles per decimeter cubed of acid of hydrogen ions. All right. And therefore, the pH is negative log of the hydrogen ions, which is negative log of 0.033, which is 1.51. Now, having said that, chemist, you then got to think now, pause now. You know, you're on the test, you're thinking, right, so what I got to do is think, does that make any sense? Yes, it does, because the pH is less than 7. And it's an acid, it should be less than 7. Okay. So anyway, here we are. This was the one here where we ended up on last time. I think we started this one or just about to start it. I think it was coming at the end of the hour. So this one here then is how you calculate it if it's excess acid. And let's do this one here. So this one here, hold on. Got to find my calculator. Got to do everything live here. Still using my trusty TI-83 Plus calculator, which is older than most of you watching this video. Okay. So having said that, I think this was this one. And yeah, I think we'll add this one in here just now. So tell you what, I don't want to do a past paper question, but let's add this in here live. Okay, so let me see if I can copy it over. No, all right. I thought I did this earlier, but obviously not. Okay, let's see. I got, well, HCl and potassium hydroxide. Okay, so this one here, then let's get this one going here. So I've got, this is question 3. All right, I've got HCl and, whoops, potassium hydroxide like this. And so you're thinking, well, this one's easy. It's a monoprotic strong acid and just a plain old sort of potassium hydroxide, right? KOH. So therefore, you're thinking what KCl and H2O, nice 1-to-1 ratio. So I could immediately write down the fact this is balanced. Okay, I've done that. I'm going to write down C and V like this because I automatically write down C and V like this. Why? Because I just basically, it's how I organize all of the data in my mind, all right? Let's see, 100 cubic centimeters of 0.05 for the HCl. So hold on. I got 100 cubic centimeters right here of the 0.05. All right. HCl is at 50 cubic centimeters of 0.5 KOH. What's that? 50 and 0.5. All right, so hold on. Again, not wearing glasses this week, chemist. And was that 0.5? Did I get that right? I think I did. Yeah, 50.5, 100 and 0.05. All right, then. So first thing I need to do then is step 1. Now, chemist, how I teach this is this. Look, it's algorithmic, meaning once you've done one, you've done them all. So what you got to do is come up with a system, like a template that you can follow, like a recipe, if you would, you know, and then you can just grind these out on the exam if you're doing past paper questions, okay? So step 1 is I'm going to calculate which reagent is in excess. Is in excess. All right, and so, you know, C equals N over V. Now, when I do these on the exam, what I teach chemists is this, is that you're writing down all the steps so the examiner knows what you're doing. They can follow the logic on your paper, okay? It gives you as many points as possible. And so you put down the moles of HCl like this is going to be what, 0.05 times 100 over 1,000. Now, right, I think that should be 0.005, but let me check my mental math this morning, right? Actually, this afternoon, 0.05 times 100 divided by 1,000. Yeah, I got 0.005. Right now, 0.005 right here, moles of HCl. All right, this one, check. And then you've got the moles of OH minus, because obviously potassium is a spectator ion. So what, 0.5 times 50 over 1,000 like this. And let's say 0.5 times 50 over 1,000 is coming back as what, 0.025? 0.025 moles of potassium hydroxide. Now, step one, right? So step two. So what I teach chemists is this, is that write down the steps to the examiner so they can follow along. You know, oh, this is what they're doing now. They got the moles of acid, the moles of base, and therefore step two is that they're going to calculate, obviously, 0.025 is larger than 0.005, and so calculate, put down moles of hydroxide ion in excess like this. All right, then. So here we are. The moles of hydroxide ion is 0.025 minus 0.005. Whoops, hold on. I can write 0.005. Slightly better than that. Hold on. 0.005 like this. And so this is going to be what, 0.02, right? By mental math right here, 0.02 moles of hydroxide ions. Yeah. All right, then. So sidebar. Okay. This is like the one thing that I like about bit paper as compared to other products, is because they have like lots and lots of little tools in here that you can use to make, you know, working online a whole lot easier. All right, so step three. All right, I need to get the concentration of hydroxide. And so on this one, chemist, it's got to be additive, right? The volume is additive. This is the tripwire. And so you're thinking, right, the hydroxide ion like this concentration is moles over volume. Now, I'm going to actually write down VT. So this is the total volume. All right, just to keep it straight in our heads here, 0.02 over, hold on, it was 50 and 100, right? So was it 150 over 1,000 like this? And so hydroxide ion is going to be 0.02, yeah, divided by 150 over, whoops, over 1,000. And I got 0.133. All right, so 0.133 moles per decimeter cube like this. Right, now, again, on this one, chemist, okay, on this one, think, what's the examiner asking you to do? What are they testing? Well, when you come to the end of this bit, now you need to, in step 4, you need to get the pH of the solution, right? So in step 4, you need to get the pH. Now, you can either, you can do pOH is negative the log of the hydrogen ion concentration, and then pH plus pOH equals 14, or you can do this one. You can say the OH minus concentration is Kw over, sorry again, this should be the H plus concentration, got it. So the H plus concentration like this is Kw over the hydroxide ion concentration, which is 1 times 10 to the minus 14 over 0.133. And so I'm going to get the H plus concentration is, hold on, 1 to the negative 14 divided by 0.133 is, I got 7.51. Yeah, 7.51 times 10 to the minus 14. Okay, and I'll just scroll up a little bit here to get everything onto the same tile here. And so therefore, yeah, the pH is minus the log of the hydrogen ion concentration, which is minus the log of 7.51 to the negative 14, which is, hold on, I'll do these live, negative the log of, we said what, 7.51? I had what, 13.12? So what, 13.12? Now, because you know that you got to take the pH, you always report the pH value of the two decimal places, right? Stop and think now. I think, yeah, potassium, was it potassium hydroxide? Yeah, potassium hydroxide is a really strong base. It's a group 1 hydroxide. Therefore, it would make sense the pH, if it's in excess, the pH would be greater than 7. So, yes. All right, then. So, chemists, what we did then is, because I want to move on to past paper questions, is this one is we've done the pH calculation with excess acid present after you added the acid and the base together, or excess base. All right, done this one. So now let's come down to a question here, right? So on this one here, all right, I got these up on the big screen on my trusty iPad here because, you know, I love Apple products. All right, Apple products are just awesome. All right, I live in the Apple universe. Okay. Anyway, shameless plug. So it says the ionic product of water Kw is 2.93 times 10 to the minus 15. All right, at 10 degrees C. Okay. And what they're asking for is, what's the correct expression for Kw? Okay, so down here, I tried to get all the questions, as many questions as I could onto the page here. And so Kw, the ion product of water, well, isn't it? It's always what this one is referencing. So in your notes, chemist, you're thinking, right, I got to reference this now back into my notes, consolidate my knowledge. It's the auto-ionization of water. This is what they're going after, because water is amphiprotic, meaning it can act as an acid and a base. And so I'm going to get this like this. And so Kw then, Kw is going to be products of a reactants. And I'm going to scroll this up just a little bit to get on right there. Look. It's H3O plus times OH minus over, technically, H2O quantity squared, but we know that you don't bother putting in liquids or solids into the equilibrium expressions because for all intents and purposes, they are the concentration is constant, all right? So therefore, I'm saying that Kw is H3O plus times OH minus, but I also know the H3O plus is written the shorthand as B and H plus, and so therefore it's got to be C, all right? It's got to be H plus times OH minus like this. And so this was the first one. All right, now the second one then, okay, chemists, right? Second one is, look at this one. It says calculate the pH of pure water at 10 degrees C. Right, now, you gotta stop and think, I wonder what they're getting at. Well, it's not going to be 7. because that would be too easy, right? So you're thinking, oh, it's at 10 degrees C. And so remember, like a couple of lessons ago, we said that the Kw is temperature dependent. Meaning, didn't we say that this expression down here is actually endothermic? So therefore, dependent. So therefore, the value of Kw depends on the temperatures. This is 10 degrees C, right? It's not room temperature, 25 degrees C. And so therefore you're thinking, aha, right then. So using the expression here, I'm going to say that Kw is H plus times OH minus like this, but H plus has to equal the OH minus concentration. Why? Because it's a one-to-one correspondence, chemist. And so down here, look, if you do the proton transfer right here, the PT, the proton transfer, slide this one in down here, right? It's a one-to-one correspondence. So this is why I can say this. Now, I'm going to set this equal to X. In some of the mark schemes I've seen, what they do is they set this, they say Kw is X squared, and they say, you know, H plus, they say Kw is H plus squared because H plus concentration is equal to the hydroxide concentration. Yeah, I don't really like that one. And the reason I don't like that one is because yeah, it isn't H plus squared. It's H plus equals hydroxide concentration. Because saying it's H plus squared means you think there's two versions of H plus on the right-hand side. No, there isn't. And so mathematically correct here for my mathematicians out there, Kw is going to be X squared. And so X is going to be the square root of Kw, which is the square root of, what was that? Hold on. Got my contacts in this week, Cam, just got to bear with. 2.93 times 10 to the minus, what's that, 15? All right, ding. Okay, so therefore X is equal to, hold on. I got the square root, we said what 2.93 to the negative 15th, right, like this. I go a 5.41 to the negative 8. Is that what we got? Yeah, okay. All right, 5.41 times 10 to the negative 8, which happens to be equal to the H plus concentration, which is equal to the hydroxide concentration. Yeah, I know I'm being nitpicky about what X actually means, but anyway, so the pH then is negative the log of the hydrogen concentration, which is, split this over here, negative the log of, 5.41, 10 to the negative 8. So let's say negative the log of what, 5.41 to the negative 8, like this. Are we getting what, 7.27? Right, 7.27. So my answer then, pH of water at 10 degrees C is 7.27. Right. So this was this one, right? So again, on this one, look, the reason why I picked this question here, chemist, is because they'll ask you this one because they're hoping the odds is going to write down pH equals 7 because you think the pH of water is neutral. But no, we went over this one a couple of lessons back. We said pH, the Kw is temperature dependent, therefore the pH is going to change based on temperature. Right. Now then, it said, suggest why this pure water at 10 degrees C is not alkaline. All right then. So hold on. Oh, it's because, all right. It's because the concentration of H plus, did we say is equal to the concentration of OH minus, all right, which is on the previous board, wasn't it? 5.41 to -8, right? So 5.41 times 10 to the -8, like this, right? And so therefore, actually, it is neutral. So this is a reason why it's an alkaline. It's neutral because the H plus is equal to the OH minus concentration. Now, again, on this one, chemists, what they're asking you, the reason why they're asking you this one is because they're trying to get you confused and thinking, oh, because the pH is not equal to 7, it's either got to be alkaline or it's got to be acidic. But all right, it's neutral because the hydrogen ion concentration is equal to the hydroxide ion concentration. You get the same number of moles of hydrogen ions and hydroxide ions, okay? Let's see, can I see this one real quick? Calculate the pH of what's that, 0.00131? Hold on. I got the big version over here, actually see it. What's a 0.0131 moles per decimeter cubed of calcium hydroxide. All right, so what they're saying is, so again, on this one, and why I look at this straight at the back, go calcium hydroxide is this. All right. So this means I'm going to have 1 calcium and I'm going to have 2 hydroxides for every mole of calcium hydroxide, okay? It's a 1-to-2 ratio. So this right here is a 1-to-2 ratio. And so therefore, they say that the concentration of calcium hydroxide is what? So what point was it? 0.01? Yeah. 0.0131. All right. This is for calcium hydroxide. And so therefore I'd have to double this. So 0.0131. If I double it, it's going to be what? 0.0262. So 0.0262, like this is the concentration of my hydroxide ions. Yes. All right then. So therefore, the concentration of my hydrogen ions is going to be, aha. Now this bit, again, chemists have been really sneaky on this question because I'm going to write down Kw over the hydroxide ion concentrations. And then what they're hoping that you're going to do is that you're going to write down Kw is 1 times 10 to the minus 14, all right? But it was actually given in the previous question as, what, 2.93 to negative 15, is that it? Yeah, 2.93 to negative 15. Hold on, 2.93 times 10 to the negative 15, like this, over 0.02, hold on, 0.0262, like this. And so H plus is going to be, all right, hold on, 2.93 to the negative 15, right, divided by 0.0262. I got 1.11 to the negative 13. Yes, no, 1.118. Okay, I got contacts in this week, so 1.118 times 10 to the negative 13. It's a concentration of my hydrogen ions. And so the pH then is just minus the log of 1.118 to the negative 13, which is equal to 1.118 to the negative 13. Dang. I got 12.95. So I've got 12.95 out to 2 decimal places, and the big screen here. Yes. Okay, got that right. Now, again, chemistry, if you look at this one, you think, well, the reason why I picked this one is because the calcium hydroxide, it's a double hydroxide. It's a 1-to-2 ratio. And they'll put one of these on the exam because they're hoping that, number one, you don't see that, okay? But also the fact that Kw is temperature dependent. It's not 1 times 10 to the minus 14. It's 2.93 temperature minus 15 at 10 degrees C. Okay, then. So this one. All right, now, hold on. I'm going to peer into the screen and read this. It said the 0.0131 mole per decimeter cubed calcium hydroxide solution. All right. In part D was a saturated solution. Now let's say the student added 0.0131 a moles magnesium hydroxide into a decimeter cubed of water, 10 degrees C, and stirred this mixture until no more solid dissolved. So translation, this means they made a saturated solution. Means both are now saturated solution of calcium hydroxide and also magnesium hydroxide. All right, so I've got calcium hydroxide like this versus magnesium hydroxide like this. Okay, so something's going on with hydroxides. Predict with the pH of magnesium hydroxide solution formed at 10 degrees C is larger than, smaller than, it's the same as the pH of calcium hydroxide as 10 degrees C. All right, now, hold on a minute, chemists. So they don't really, they don't give us any more information in part E than they did in part D. Meaning in part D, it was a 0.0131 mole per decimeter cube solution of calcium hydroxide, and it's the same as 0.0131 moles per decimeter cubed of magnesium hydroxide. They're both plus 2 oxidation states in metal, which means that you're going to get the same exact concentration coming out of hydroxide ion, the same value going down. So let's see. Now, what I'm thinking is, could it be a synoptic link? Could it be something to do with the solubility of the hydroxides? Okay. So, having said that, solubility of the hydroxides. Okay. Group two. Like magnesium, or then calcium is below magnesium, right? And so I'm thinking, hold on, is it the hydroxides versus the sulfate one? And so I'm thinking, is the solubility of the hydroxides, oh, hold on. Doesn't the solubility of the hydroxides increase going down the group and the sulfates increase going up the group? Is that it? So I'm tying in now to the module in group 2. So I'm saying that this is my solubility. All right. Right. So this is what I've got so far. So therefore, I'm thinking, all right, yeah, I think this is it. It's the magnesium hydroxide is less soluble. And the calcium hydroxide, therefore, going further down the group, is more soluble, right? So I got this going. Right, so therefore, if magnesium hydroxide was less soluble, then you would have, hold on. If magnesium hydroxide is less soluble, then wouldn't you have, hold on, a pen that worked, hold on, is less soluble. Trying to get the word soluble out, soluble. Then you would have less hydroxide ions present. well, dissolved in the water, wouldn't you? And if you had less hydroxide ions dissolved in the water, then therefore you would have more hydrogen ions dissolved in the water, because Kw is H plus times OH minus. And so because magnesium hydroxide is less soluble, less hydroxide ions are present, which means that the concentration of the hydroxide ion goes down, which means the concentration of the hydrogen ions has to go up because Kw is constant. Oh, here we go. And so because Kw is constant, this therefore means that I'd have more hydrogen ions, and so concentration of hydrogen ions would increase. Therefore, I would have a lower pH because it's more acidic. So therefore, I'm thinking that the pH would be lower. All right. So how do we do on this one here? The pH is low, all right. So chemists on this one, look, do you see what we did in this one, right? Is that we tied in the concept from this module to a previous one, you know, like the one on group 2 and group 7, like your teacher's probably done, like, you know, they probably did redox reactions, and then group 2 and group 7 in year 12, and in year 13, now we're taking that concept of the group 2's chemistry, and we're now applying it to acid and base chemistry in year 13, right? Fair game for the exam. All right, then. So looks like we're 5 for 5 here. Doing good. Who are we doing on time? Doing right. So, all right. Ding, 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 ding. Ooh, okay. So have I moved on? It looks like I moved on to a new topic here. So on this bit then, chemistry, right? So moving on then. All right, here we go. All right, on this one right here. And so we're going to have a little discussion then about, in fact, let me just put a new page in like this. Probably going to be easy if I just do a new page. All right, so here we are then, chemists. Right, so note time. All right, so let's go a quick look at weak acids, and then we'll start doing some pH calculations on weak acids. All right, so weak acids, chemists, here we are then right here is, oh, that's good, is this one here. So a weak acid, they tend to be organic acids, tend to be organic acids. So, you know, last time we did the 7 strong acids, you know, hydrochloric, hydrobromic, hydroiodic, the 3 halo acids. And then we did the 4 oxy acids, sulfuric, nitric, chloric, and perchloric acid last time, right? The weak acids are those that tend to be organic acids. So, for example, what they're going to do at the A level is that they're just going to give you something simple, like they'll give you methanoic acid, like this, or they'll give you ethanoic acid, vinegar. All right, if you're wondering why do they always use ethanoic acid, it's because, well, it's an easy acid to use. You know, I mean, practicals, easy, it's just vinegar, all right? So this is the reason why they tend to use ethanoic acid a lot. So this one right here, this is your ethanoic acid. And the other one that you'll probably see, and they'll stop at this one, you get propanoic acid. Now, the reason why they use propanoic acid is because we'll talk about this one probably like next time, is the strength of the weak acids, okay? So propanoic acid, let's get all the calculations done today. So anyway, if I had in science solution then, All right, here we are like this. Boom. Right. Inside solution is ethanoic acid. Then I'm thinking I'm going to draw my equilibrium like this. So the position of equilibrium lies all the way over to the left. All right. And use my ethanoate ion like this and my H plus. Right then. So Ka is just going to be, right, this, right? Now this is my Ka value expression. So if I come over here now, it says, all right, let's say, actually, did I thought I had a question on, right, hold on. I thought I had a question on pure acid. Right. I tell you what, I want to modify this one, the pH. Oh, let's just do the pH of a pure weak acid. So I'll use this one. pKa is 4.76, right? And so for ethanoic acid, because this is going to come in handy now. Try to write the word for ethanoic acid like this. So for ethanoic acid, like this. Okay, here we are. Right. We said what the pKa is, what, 4.76? Is that what I wrote down? Okay. Right. So if I said, right, the pH of a pure acid, like so, hold on, can move my video link out the way of the chemist. All right, then. So using this expression up here, then, all right, so 4.7, let me write it like this. So before I do that, let me move this down here, chemist. Would you agree? Would you agree that it is a one-to-one correspondence? Now this bit becomes just like slightly important here. So here we are, one-to-one correspondence, right, between the molecular acid and the anion, ethanoate, and the molecular acid as an ethanoic acid and the hydrogen ion. Right. The reason why I say that, because it's a one-to-one correspondence. If it's on zone, all right, then you think it's like, acids in the beaker, right? Your pK is 4.76. All right. I can say this. I can say the 4.76. So using this expression here, then, is going to be, right. Well, see this ethanoate and hydrogen ion, it's a one-to-one correspondence. So I'm going to put down here, I'm going to say this is equal to this on its own at equilibrium, which is equal to X. Okay, so this is where the X squared comes from over the concentration of this. And so again, I'm really nitpicky. I just have to admit, I'm like nitpicky when I see this, like, 4.76 equals X squared in the mark scheme, and they haven't put this bit in over here. Well, I do raise an eyebrow and go, well, not really chemically correct. But anyway, this way is. So look, all right, so X then is going to be, well, Ka times the concentration of the weak acid right here, which is going to be what, 4.76 times, let's see, I'll just pinch this value. I think was it 0.2 molar, times 0.2 moles per decimeter cubed. So I'll put it down here again. It's 0.2 molar per decimeter cube, like this. All right, just keep the numbers same as it is in like the next bit. All right, then. So now what I can do with this is I can say x is equal to, all right, hold on. I got to take the square root of this. So can I do this if I've included everything? All right, square root of that, which is, let's see, I got the square root, second button, square root of 4.76 times, hold on, times 0.2. And so I've got 4.76 times 0.2. Was it 0.2? Yeah, 0.2. All right. So I got this. Hold on. I'm going to divide this, write this down real quick. 0.975. Okay, so then I've got to take the negative log of that. So hold on, negative the log of 975. Yeah. Okay, hold on. Ding, 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 ding. So just right there, pH of this 4.76x squared of this. Right. Yeah, okay, we should try this again. Hold on. Maybe I typed on 4.76 like this. Yeah, times 0.2. All right, is this. I got 0.952. Right, take the square root of that. Second button, square root of 0.952 is, yeah, that. And then I've got to take negative the log of that. Of 0.975, ding. I got 0.01. Okay, a bit low from what I wanted, 0.01. Or I'll probably find out that I made a mistake somewhere. All right then, so, but bottom line is, chemists, is what I said is the H plus ion concentration is equal to the ethanoate ion concentration at equilibrium. Yes, I'm buying that. Oh, you know what? Oh, got it right there. All right, forgot to take. Try it again. So I got what I said, that the ethanoic acid breaks bond to ethanoate ion and H plus. Yes, 1-to-1 correspondence. Therefore, you've got, here's my Ka expression here. You totally agree with that. All right, now this is your pKa. See, forgot to convert over. This is your pKa, which is minus the log of the Ka. And so therefore the Ka, which is what I wanted, was 10 to the minus pKa. That's why it was so low. Right, so about 10 to the negative 4.76. Okay, so hold on. Second button, 10 to the negative 4.76. Right, oh, there we go. All right, and so this means that the Ka value is what, 1.74738 times 10 to the minus 5. That's going to help out a lot. So therefore, this now becomes this. So let me scratch this out and try again. See, chemistry, it's always fun doing it live, but did you see what I did there, right? Is that I said, no, that just doesn't make any sense. It's awfully low, the pH value. So that now let's go back in. All right. So here we are then. So Ka is we said 1.738 times 10 to the minus 5. And so I got 1.738 times 10 to the minus 5 is, let's see, this expression up here, all right, is going to be x squared, because I defined it up here what it was, over the concentration of 0.2. And so now x is going to be the square root of 1.738 times 10 to the minus 5 times 0.2. Almost 10 to the minus 5 times it by 0.2, and I've got that 3.47 to the negative 6. All right, so I've got what, 3.47 to the negative 6, like this. Okay, now it's a bit better. Right, so x then is equal to, hold on, second button, square root 3.47 to the negative 6. Well, so hold on, give me context in this week. So hit the wrong button. See, chemists have always got to be doing it live, and so therefore, you know, this is not scripted. This is just me working on problems with you. So I got x is what, 1.86 times 10 to the 1 to negative 3. Okay, and so I'll scroll this bit down here so we can see what's going on. All right, so therefore, H plus concentration is equal to x, which is 1.86 times 10 to the minus 3. Let's see, so pH is minus the log of 1.86. Don't know what's going on with the pen. 86 times 10 to the minus 3. All right, then, which is, okay, try this time now, negative the log of 1.86, second button, e to the negative 3. Yes, okay, so much better now. I got, yeah, 2.73. Yay, got this one right then. Okay, so I have to do this for places. All right, so move my video link out the way here, move it down here so you can see what's going on. All right, then, so chemists, on that one then, right, so look, the takeaway on that one is, okay, so we covered a lot today. On the weak acids, yeah, on this slide here, I'll loop everything back in for you now, chemists, okay? It's on this one, right? The acids that the acid that they tend to use all the time is methanoic, ethanoic, and propanoic acid. Why? Because they're all monoprotic acids, number one, and number two, using Kleep's health and safety hazards, you know, like the HAZCODs, they are fairly safe to use in the lab, you know, like ethanoic acid is just vinegar. Right, so what I was getting at on this one is, on the weak acids, it's only about 0.01, it's like 1% ionized, but you're thinking on the weak acids, on its own, so this is the pH of a pure acid on its own, like sitting in the beaker, all right? You're thinking is just going to be this expression here. You're going to write down the Ka for it, which is like products over reactants, got this bit done. And then they gave you the pKa, and then they gave you the concentration, right? In the question that I made up here, right? Now, I always define chemists as being, I always define that it's the anion and the hydrogen ion is equal to X. Now, what I did, you know, all right, doing it live, you know, right? What I did is I needed to come out and actually, they give you the pKa, you had to get the Ka expression from it right here. You know, Ka is negative, pKa is negative log of Ka, so Ka is 10 to the minus pKa. This is a very reasonable expression, value, if you would, for a Ka. You know, putting in the 4.76 was like, no, in the back of my mind, I'm going, something is not quite right here, but this value here is, and then solved it for X, put it in to the pH formula, and then we got 2.73, which, to be fair, chemists, is something which is very reasonable. It's a very reasonable pH to have for a weak acid. You know, like acids tend to be around, like, you know, weak acids tend to be, say, around, say, 2.76-ish, you know. So this is why when we got the first value, it's like, whoa, that is like seriously wrong, because something didn't quite make sense from the chemistry point of view. All right. So that's called thinking on the fly. This didn't quite make sense. Let's go back in and fix that. So what we did then, chemists, is today, quite a few questions got done. All right. We basically wrapped up pH calculations. So we did the very first one was the pH of a strong acid and a strong base. It was a diprotic acid. And this is the formula that we actually use, the expression here. Okay, because chemists, it's so easy. And I'll admit that sometimes, you know, you're doing really quick. You're so used to doing monoprotic acids that you write down, you get the moles of acid and the moles of base. It's a 1-to-1, and therefore you get the excess moles of acid and base out. But the exam board will put in a diprotic. So really, it's best practice if you write out hydrogen ions and hydroxide ions give you water, and therefore you know it's a 1-to-2 correspondence between the moles of the diprotic acid and the hydrogen ions, right? So we did this one, excess acid, and we did this one with excess base, all right? And what I said was, chemists really, you know, come up with a template for doing these, like, you know, come up with your way, your steps of doing them. And after you've done one, you've done them all. There was this one. And then, yeah, we did some past paper questions, and the past paper questions I picked, chemists, were really done to highlight the tripwires. You know, the first one, question one, got my video link in the way here. All right, the first one, yeah, I picked the one where Kw was not at room temperature. Okay, this one here. Let's see, and then calculate the pH pure water, because again, this is the tripwire. They're going to try to get you not to use the correct value of Kw. All right, because most students would write down 1 × 10⁻⁴, right? Now, having said that, we then look at the fact that, yeah, it's neutral chemistry. Even though the pH is less than 7, it's neutral because the hydrogen ion concentration is equal to the hydroxide ion concentration, okay? Then we did a really simple one where you just calculate the pH of calcium hydroxide. I picked that one because it is a 1-to-2 ratio between the calcium hydroxide and the hydroxide ions. All right, this one here. Now this one here, E, yes, I picked this one because chemists, on this one, it is a synoptic link into module 2, and into the module in year 12 on group 2 chemistry, okay? So you needed to recall the solubility of the hydroxides and the sulfate. All right, this one tends to be, this is my A-star question of the day here, okay? Synoptic link into previous modules. And then after that, yeah, we just wrapped up with pH calculation of a weak acid. So where this is leading us to is this, chemists, is next time, what I wanted to do next time is we'll do titration curves next time. No, actually, yeah, next time, let's do titration curves next time. All right. And I'll show you the 5-point touch system for drawing a pH curve of weak acid, strong base, a weak base, strong acid, strong base, all the combinations you can think of, and even the one with the weak acid, weak base. I'll show you what all the curves look like. All right, and then I'll show you the 5-point touch system for drawing a pH curve, a pH titration curve of a weak acid and a strong base, which is always on the exam every year. Okay, so having said that, chemists, you have a good week, and I will see you next week. All right, so everybody take care, and I'll see you next week.